Okay, so chapter 7, if you'll notice the title to it. Oh, rational functions. Anybody have any idea what rational means in the context of math?
Easy numbers.
We're dancing all around it.
It's not a regular.
There are natural numbers, there are whole numbers, integers, rationals, irrationals, reals,
Rational
and complex, as you now know.
numbers greater than 0 can be written as a fraction.
No, almost. Any number that can be written as a fraction.
Oh.
That fraction. It could be not positive or negative. Any number that can be written as a fraction. Now, that doesn't mean you know how to do it, but it can be. And the way you recognize it, for example, is the square root of 2 is irrational. Because if you convert it to a decimal, this decimal goes on forever, never repeats, never stops. That's irrational. A rational number is any number written as a decimal, if you want to recognize it as a decimal, that either stops, like 3.25, or begins to repeat it someplace, like 3.3 repeating. Both of those are, as you know, are rational because the 3.25 is 3 1/4, which is a fraction. The 3.3 repeated is 3 1/3. So that's how you recognize them as a decimal or whatever, but typically when we talk about rational functions, and that's in the title of something, the discussion is going to be about fractions. Because that's what makes a rational number rational, is it can be written as a fraction. And by the way, all integers, which are all whole positive and negative whole numbers, they are all rational because every one of those can be put over 1. And that's one integer over another. That's what defines a rational. So all integers are rational and all fractions that you can think of, those are rational too. When we talk about rational functions, we're going to be talking about functions that have a numerator and a denominator both written in terms of x. Or maybe one is written in terms of x and the other one is not, but those will be rational functions. Before we get to the actual looking at the functions and their graphs and their properties and stuff like that, we're going to talk about a thing called inverse variation. We're also going to be talking about direct variation because when you can see opposites, you generally understand what we're talking about better. So here is what we say when we say a direct variation. I'm going to talk about that first, and then I'm going to show you what an inverse is, which is what this thing's really about. Direct variation. Generally, you'll see something like this. And it's not always going to be X and Y. It may be a concept, it may be an idea, but you're going to see a phrase like this that'll let you know. It'll say, Y varies directly with X. And then some other stuff will follow. But this is the phrase you need to look for. The other one that would be just exactly like this would be saying Y is proportional to. X, and then some other stuff. Both of those mean exactly the same thing, and it means a direct variation. These are the equations that go with it. If you see this, this is what you write. Y varies. Varies is a verb. Verbs in math are equal signs. Y varies directly tells you you're going to multiply some constant number times X. Here's a different version of it that's very, very useful. If I just divide both sides by X, I get Y divided by X is the same number every time. Any Y and X that goes together on something varying directly, if you take the Y value and you divide by the X value that goes with it, you'll always get the same number every time you do it. So you take a Y divided by an X. This is very useful. This is where you start. Doesn't mean you always go here, but this can be a useful thing. This is where you begin when you see the phrase. Is to write, if it says direct, is to write Y equals KX. All right, I put that right smack in the middle of the board, so I'm going to swing this way just a smidgen. Now this is inverse variation, which is what most of this is, but it's kind of nice to know opposites when you see them. Inverse variation, and there's only one phrase. When they mean inverse, they'll write inverse, so there's not two different versions of it. So it'll say this. something like this. It won't always be y and x, maybe concepts, but you'll see something varies inversely with something else. Y varies inversely with x, and something else will follow, some information will follow. And when you see this phrase right here, you start with the beginning of it, there's your verb, so it's y equals k over x. Here comes the rational functions, see? Now you're starting to introduce fractions. And this is where you would start. If you see this word inversely, you got to do a division. If you see the word directly, it'll be a multiplication between k and x. And if we, this is where you start. If you see those words. And this is a very useful form. It won't always go to this, but it'll be a way for you to tell. A useful form of this is to cross multiply. You see the 1 under the y? You see that 1 under the y? So when you cross multiply, you get yx equals k. Which means that every time you multiply, not divide, every time you multiply the y value times the x value on this function, you'll always get the same number, like 8 or something. Every time you multiply a y that goes with the x that goes with it, when you multiply those together, you always get the same number, no matter what combinations of x, y you get, if it varies inversely. Following? So, take a look at example 2. No, let's look at example 1 first. Example 1, try not to look at the solution. Don't do that, do yourself that disservice. It says, tell whether x and y show a direct variation, an inverse variation, or neither one. So you're looking for one or the other of the forms. Both of these mean direct. So form, both of these mean inverse. And so what do you think the first one is?
Reverse.
Inverse. What is the second one? Neither one. Neither one works, because if you try to get x and y on one side, for b part you would get y minus x. We don't have that up here. We either have y divided by x or y times x. We don't have any subtraction. And so when you try to get them on one side, so it's neither one. How about the other one? Last one. Is it inverse? It's correct. If you solve for y, you get y equals 2x, which is this form. See what I'm talking about? Do you see that? Okay. All right, so now look at example 2. Now we've got a bunch of x, y samples from a function. We got to decide if we think it's directly related, inversely related, or neither one. So how would you start on the A part, top of page 361? How would you try to decide if A is one or the other? What would you begin to do?
See if the X are spaced out.
See if what?
The X are spaced out.
That actually isn't even necessary. It's the XY combinations this time. So we can see that if X is 2, Y is negative 12. If X is 4, Y is negative 6. What can you do to determine if it is inverse or direct? This is where the useful forms come in. Oh, this doesn't have 2 L's. What could you do to investigate whether this set of numbers represents a direct, an inverse, or none? You could, but there's a better way. This is what I said. Take a look at this. If I was to multiply y times x and get some number, and then take another y-x combination, multiply it, get the same number that I got before, take another one, multiply them together, get the same number, I know it's inverse.
So,
On the other hand, if that doesn't work, if I took a y value, a y value and divided it by the x that goes with it, got a number. If I take another y value and divide it by the x that goes with it and get the same number I got before, that would be evidence that it's direct. You see? So let's try the first one out. What is 2 times negative 12? What is 4 times negative 6? What is 6 times negative 4? That's enough evidence. I don't have to do the last one. You better do more than 2. You better make sure you get it at least 3 times. And so this is going to be concluded to be a what? An inverse. Look at the next one. What's 1 times 2? What's 2 times 4? Then it's not inverse. What is 2 divided by 1? What is 4 divided by 2? Oh, that's good evidence. 8 divided by 3? Not 2. 4 divided by 16? 16 divided by 4? Not 2. So we're going to say that's neither. You see how we investigated? The product didn't work. The quotient worked twice, but not 3 times. That's why I'm important. You go at least 3. Well, 4. You gotta get the same number every time, and we didn't. So it's neither one. It didn't satisfy this or this. Okay. So that's how you go about investigating it, is plugging it into this useful form. One y, take the y and the x and do it. You got to get the same constant every time, whether you divide or multiply it. If you don't, it's neither. And if you do, then it's whichever one fits the bill. Okay, look at example 3. The variables x and y vary inversely. Stop right there, right there. The variables x and y vary inversely. You stop right there and write this phrase, but it's for the inverse. So you stop and write y equals k over x. Don't even read any further. Write down what you're dealing with when you see the word inverse or direct or proportional. Either one of those 3, you gotta figure out what you're gonna write. Then what you do is look at what follows. That's the dot, dot, dot. And what they're gonna do is they're gonna give you one of the billions of points on this function. They'll give you one of them. How many variables are in that, by the way? What I wrote right there. How many variables are in that? 3. They give you 3. There's 3 there. They're going to give you 2. They're going to give you a sample of an x and a y that work. What are you supposed to be going to do?
Find it.
Plug them in to find k for this particular scenario. So the next thing they're going to give you is a snapshot of one of the points. We got y equals 4 and x equals 3. So we write this. 4 equals k over 3. And before we do anything else, we go about finding k. Since this is a fraction and we understand the 1 under 4, it's going to be 12 equals k by cross multiplying. Do you agree?
Yes.
Then you come back once you know what k is from that snapshot and you rewrite it with y and x back in it. This is what it is when they say write an equation which represents the situation. So the variable, it says the variables x and y vary inversely. As soon as I see that word inversely, I write y equals k over x. Then I look for a snapshot. I got a y value and x value. Plug it in and solve for k. It says write an equation that relates x and y. That's what I've accomplished so far, right there at that arrowhead. That is the equation that relates x and k. I'm sorry, x and y. Do you see that?
Yeah.
After we find k, we put it back in where it goes and put x and y back in where they go.
Equals 12 over
Yeah,
x.
yeah, I screwed that up. I hate it when I'm talking and trying to do math. Should be 12 over x. Yes, thank you. Thanks for catching that. That was bad. I had to reverse those talking. Okay, so that's our equation. That's the correct one for this one. Then it says, then you got one last thing to do. Then find y when x is negative 2. So y is equal to 12 over negative 2. That would be. So that's a part of the answer, and so is this. You start here because it said inverse. They'll give you a snapshot, you find k, you rewrite it, putting k where it belongs, which is what I didn't do the first time. K where it belongs, and then use that to make a prediction. So write this. This isn't part of the answer, but this is where you begin. Write that. Find k with your snapshot. Use that to find some value, some specific value that wasn't given to you there. These are the 2 answers. This is the equation you were asked to write. This is what the value of y is when x is negative 2. Did y'all see that sequence? Okay. On the page. And we got a story problem. And this is where things like x and y are not going to be mentioned. It's going to be something else. And you got to give yourself, you got to tell yourself what you want to call those things. So here's our scenario. They're telling you what to call it, actually. It says the time t. So they're telling you what to call time, it's little t, that it takes for a group of volunteers to build a playground. All that stuff is peripheral information as far as the math goes. What you have to do is be able to whittle things out with your eyes and your brain. It should, if we're going to adjust the math on this, it should say that time varies inversely with n. T inversely with n. Can you see all of that? Extracted out of the first sentence? Now they're telling you context. They're going to try to build, they got volunteers, and however many people show up is n. The time it takes them to construct this playground that you're looking at there is the amount of time, from the time they open the boxes until it's all set to go. And those 2 things are related inversely. In other words, the more people you have show up, the less time it takes to build it. And so as one gets bigger, the other gets smaller. That's a typical inverse relationship. But the main thing for doing the equations here and then doing the stuff is the first statement says t varies inversely with n. And so we would write this to start with. T varies inversely with n. Y'all see that? Substitution for x and y and the order it came in and stuff? Okay. Then it says, make a table. Oh, we got to find more than one value. Make a table showing the time it would take to build a playground when the number of volunteers is 15, 20, 25, and 30. Oh, left. Some information at the top I didn't get. It takes a group of 10 volunteers 8 hours to build a playground. So this is our snapshot. You understand why I put where I did, what I did, and did I do it right? Make sure you're checking on me here. Cross multiply tells me that 80 is k. So the equation I'm going to use is t equals 80 over n. Remember, this is time and this is number of volunteers. And now they want us to produce a table. We'll put t here and n here. And what are they going to give us?
15, 20, 25, 30.
Yeah, but what does that represent? Volunteers. 15, 20, 25, and 30. So that's down here. 15, 20, 25, and 30. So that's our volunteers. And now we're going to use this to generate the time it's going to take for every one. What's 80 divided by 15? That's what we got to do to get this number. Go ahead and give me a decimal to maybe the nearest tenth.
5.3.
Is it 5.3 repeated?
Yeah.
Okay, so I'm going to put it down that way so that we know that's a third of an hour. Okay? When 20 volunteers show up, it's going to take 4 hours. 25?
3.2.
Does it stop there?
Yeah.
Okay. And 30?
2.6 repeated.
Okay. So if we were going to go hours and minutes on this, which we could do, what's a third of an hour? 20 minutes. So 5 hours and 20 minutes here, 4 hours here. What's 2/10 of an hour?
3 hours and 12 minutes.
12 minutes. 2/10. That's what this is. The same as 1/5. 1/5. If you divide 60 by 5, you get 12.
Yeah.
So it's just going to take an extra 12 minutes. This will take how long? 2 hours and 40 minutes. And you can see as the number of volunteers goes up, the amount of time it takes to build the thing goes down, which you'd expect. So we're saying that the notion of number of volunteers and time are inversely related because as one goes up, the other goes down. We good? Okay. That's the end of that section. Do you have homework? Yes, you do in this section, but I'm also going to do another one because that was way too short for a day. And there's only 9 questions on that exercise. 7.2 is those where we're going to get into the nitty gritty, where we're going to actually start doing some algebra 2 type math. This was not too bad. You can do this. You can do this section with, if it takes a little bit longer, but you can do this section with 5th graders. I don't mean to be insulting, but this is not hard. Okay. All right. So let me erase this. We're moving on to section 7.2, and now we're going to get into the graphing of what rational functions look like, and the notion of asymptote. An asymptote is a line. Well, not always a line, but will. An asymptote is a line that the graph approaches as x does something. You'll see what I mean. With rational functions like this one. This will be the parent function for us. The parent function for all rational functions is this. This is the simplest possible one. Everything grows from this. That's the parent. Now, when we start talking using words like parent function stuff, you can bet there's going to be some transformations here. But you guys are really good at reading transformations. You guys all nailed that on the test, it seems like. I didn't see hardly anybody who did that. So that shouldn't scare you at all. And this is the parent function, and the graph of the parent function looks like this. It comes down, it uses the axes for asymptotes. It comes down like that in the first quadrant. Down like that in the second quadrant. So it never touches any of the axes. Now let me tell you why. And hopefully you'll remember this. I don't know if you will, but I hope you will. The reason why it never touches this axis is because that is the location where x equals 0, right? Can you see that x cannot ever be 0? You can't divide by 0. This one never gets hit because this is the location where y equals 0. And I'm here to tell you, this is a little bit more obscure. I'm here to tell you that a fraction will never, ever be 0 unless its numerator can be. And this numerator can never be 0. It's always going to be 1. So y equals 0 can never happen because this will always be 1 over something. Even if it's something really big, it'll always have some value. Never 0. That's why this one is never hit. So x can't be 0 because you can't divide by 0. Y can't be 0 because this fraction will never be 0. It will never have a y value of 0. You with me? So the axes are asymptotes, and that's what it looks like. And by the way, on this particular one, this point right here where it tends to bend and start approaching the other one, and this point right here, this is 1, 1, and this is -1, -1 for the parent. Okay? All right, so now what we want to do is compare the graphs of 1 over x to 4 over x. So that's the parent. Here is one of the daughters, and we want to see how the graph compares. Whoops, I'm not going to use F, I'll use G, so that it's different from the parent. I'm going to say G of x is 4 over x. Can you describe, before we move on, can you describe the transformation of the parent that is? Vertical stretch of 4. Because this right here is the same as 4 times 1 over x. If you think about that, that's over 1, so there's 4 times 1 on the top. So that's 4 times the parent. Do y'all see that? Recognize that as a coefficient? It's not only a vertical stretch, it's also a horizontal stretch because, I don't want to go into that. Just tell you what's going on. What's happening here is so that we can compare the parent on the same grid. If I put the parent here, like this is the parent graph, comes down here at 1 and goes out like that. I know I'm making it a little bit exaggerated, like that. If that's the parent, then this one will hug those axes too, but it will come out and be a little smoother. This distance from here to here will be greater. This one will come out like this. Because you have pulled it this way, you've also pulled it that way. I know you're going, what? It's both? Yeah, it is in this case. Because it's just a constant on the top. It kind of affects both of them. And it's kind of a cool thing. And probably, I don't know if you'll find this useful. You may or may not. But this vertex right here is 1, 1. This vertex right here, in this case, is 2, 2. In other words, I went out twice as far here and twice as far here. It's not really the twice that's important. Whatever you multiply this by was 4 times 1 over x. The square root of this will be the number of diagonals you will count out to get to your turning point. That you won't find that in any math book, but I proved it, so I'm convinced. I don't put it like that. It just helps me graph. If I got to whip one out really quick, first of all, the black parts of the transform graph are going to be a little bit below the blue parts here, but the place where it turns is going to be the square root of the multiplier. As far as counting diagonals out. Diagonals from the origin out. Here's something to know. Okay, so that's example 1, and that's how we compared it. It appeared to be kind of a vertical and horizontal stretch at the same time. It kind of is. It just moves. So whenever you multiply it by a whole number, it just takes the parent and moves it out. If I were to do this function, h of x equals, let's say, 1 over 2x, now I've got a vertical shrink of a half. Right? You see the 1/2 times 1 over x in there? Can you see that? And that's going to be really tight. If this was the parent coming out like that, then the daughter one's going to come in like this, and it's going to turn hard like that. So that this is the square root of a half instead of the square root of 1. You see? All right. Then if you take a look, that's your vertical stretch and shrink. It also serves as horizontal. Example 2. This has got a lot more to it, a lot more transformations to it. But still, it shouldn't spook you because you guys are good at this. And it's because we've drilled and killed you on it. We won't take credit for it. You're really good at this. You become good. So here is one. It's got a lot of transformations to it from the parent, and it is -4 over x plus 2 and then -1. And this, we'll call this g of x. This is a daughter of that. Can you name the transformations?
I guess what's left. Down 1.
Okay, that's a good one.
Yeah.
Left two, right two.
Um,
No, left two.
yeah, left two.
Left 2? Uh-huh.
Is there a reflection in the x-axis?
Reflecting the X, yep. Is it reflection on the Y? X?
I think it's y, right? Because x is on the bottom, so it's affecting the y, right?
You know what? I don't know. Hang on just a minute. Let's see how they're gonna read this. I mean, it could be interpreted this way, where you multiply this function, just this, oh, no. That would make it negative X if it were a reflection of the Y. The X part would be negative.
So it's reflection in X.
This thingy right here, this part right here, and then this happens, this is actually just making this fraction, the whole fraction negative. And that's a
Reflection in X.
reflection in the X, yeah. But think about the parent function. Would it matter if you reflected in the X or the Y?
Yeah. Because it put it in the left and bottom right.
Yes, it would. No.
Would it?
Yeah, because it makes it like that.
No, what is it both the same?
Now look at this. If I take that parent graph and reflect it in the X-axis, that means that branch comes down here and that branch comes up here. Does that make sense if I reflect in the X?
Yeah.
All right, now think about reflecting in the Y. That means that this branch comes over here and this branch ends up over here. So that's kind of nice. You don't have to figure out. It's just going to be a reflection. Okay?
So we just right.
So this thing is a reflection. I'm going to reflect it in the X. As far as the result goes, it doesn't matter. And then what? Is that it? Vertical stretch 4.
Does the reflection in the x-axis, that negative effect it going left or right? Like, does the negative distribute to the +2?
No, it's just a negative fraction. If this thing could belong right here, that would be fine. Okay? All right, so when you do this up and down, left and right business right here, what it actually does, folks, is it picks up these axes, which were asymptotes before, and moves them, so this corner right here, somewhere else, so to speak. Take a look. We're going to go down 1 and left 2. Down 1 and left 2 puts the corner right there, where it used to be at the origin. See what I'm talking about? These are asymptotes now. And it was pulled out because of this vertical stretch and reflected. So instead of being here and here, it's going to be here and a little bit wider like this. Where this distance right here is 2 diagonals because that's the square root of 4. Did you catch all that? Yeah.
When we were graphing on our assignment today, P wants to move the axes like that and show us like that's what we did.
No, I don't want you to move the axes. I want you to leave the axes where they are. What I'm saying is that the corner that it used to wrap around and be symmetric to has now moved to here.
Okay.
And you got to show that with dotted lines.
Yeah,
Leave
that's
these
what I
solid.
was saying.
What's that? Yeah, leave these where they are solid and then dot these. Why do we dot them? Because they're not really part of the graph, but they aid in getting the graph correct. And so we dot them. And it's just that the corner that used to be there with the parent, the corner where the asymptotes join, is now here. We went left 2 and down 1. Does that make sense? Was there a question? No? I thought I saw your hand. Okay. And you don't need to be super accurate with this. You don't. It's just give you a gist of it. That was a multiplier of 4, so I came out 2 diagonals because the square root of 4 is 2 and tried to hit that as I went around. That part doesn't really matter to me. It's that you get it in the proper quadrants because of the negative sign, which we put them over here in the 2nd and 4th, and get your axes moved where they belong. Not axes, asymptotes. Yes.
So then, when we write it down, do you want us to write reflection in the x-axis, or do you just want us to write reflection?
Choose one. Yeah. Okay, so that's how we do example 2, and you can take a look at the graph that they've got there. They actually plotted some points to make it more accurate. I don't think that's necessary, especially if you're producing one on paper for me. That's not necessary for me. It might be necessary if you do this in Big Ideas Math. That's something to look for. Okay. We've got example 3, 4, and 5. 5 shouldn't take too long, but these 2 right here are kind of interesting. Example 3 gives you a rational function that's not like anything you've seen before. This one right here, even though there were a lot of them, I think a lot of you were pretty good, almost instinctively. I might not have to show you anything, how to read these transformations when it's in this form. But now rational functions come in other forms as well that aren't easy to read. I'm going to teach you how to do that too, to read those. So I've got a new function, which is a transformation of this one, but it's written like this: 2x plus 1 over x minus 3. That one's tougher to read. You might say, well, it's going to go to the right 3, but then with this plus 1 up here, right here, and that 2 might be a vertical stretcher, but where does this? I'm just going to tell you how it goes, okay? Because it's Friday and I've got to condense this a little bit so I get it all in. When you have it in this form and the transformations are not so easy to read, everything's obscured and foggy, this is a way out of it. What I told you before is we need to figure out where this corner of asymptotes is going to be, and then perhaps use this right here. This seems to be a multiplier, and there's another problem too, the top and the bottom. That causes wrinkles and things. You can't read it. So maybe a point or two from your graphing calculator or something would be helpful to make sure this thing opens properly. But I can tell you how to look at this kind of thing and find out where those asymptotes are. The vertical asymptote, you can call it that. The vertical asymptote will be where the denominator is equal to 0. In other words, when x equals 3. That right there is going to be a vertical asymptote. Where the denominator is equal to 0, where the x value that causes you to divide by a negative, what causes you to divide by 0, that x value will be a vertical asymptote. So I can tell you this right now by just looking at the denominator that the vertical asymptote is going to be right here. Okay, you with me? Because that's where the denominator is equal to 0. Same thing here. This vertical asymptote, when it was 0, was where x equals 0 was a vertical line at x equals 0. Same thing here. It's a vertical line at x equals 3. The horizontal asymptote is found by taking this number over this one. It's the coefficients. So this is understood to be 1. So y equals this fraction, or in this case, whole number. I better write down how you do it so that it looks like this. You put the numerator, leading coefficient, divided by the denominator, leading coefficient. Y equals that will be your horizontal asymptote. So in this case, y equals 2 over 1, or 2. That's a horizontal line. Horizontal asymptotes, horizontal, y equals represents them. We go up 2 and put it there. That's where things move to without being able to read a left certain amount and up a certain amount, or up or down. You don't do that. This time you look at the function itself. Set the denominator equal to 0 to find the vertical one. Take the leading coefficients, one over the other. Y equals that number, whatever that fraction is. That's going to be your other one, the horizontal asymptote. Now, notice that there is no negative on the fraction anywhere. No negative in the numerator, making the numerator negative, or no negative here. It'll usually be here. There's nothing there, which means it's going to occur in the same quadrants created by these asymptotes that the parent did. These right here. We got a 2 multiplier, so it's going to be a little bit wide, not much, a little bit. And the parent. And again, I really don't care about that. Get it in the proper quadrants, get your asymptotes in the right place. You see how you find those two in this situation? Okay. Had there been a negative right here, then you would have put your graph in this quadrant and that one. Y'all see? We clear on that? Yeah.
So to find the vertical asymptote, did you set the x to 0, or?
You set the denominator, the vertical asymptote, you take the entire denominator, set it equal to 0, right? Equals 0, and solve for x. And that location, that x equals whatever you get, is going to be the vertical asymptote. Okay? Let's try that. Let's get another g function. I'm going to erase these rules and see if you can tell me where the asymptotes belong on this. If I have, I'll erase this too. If I have 8x plus over 2x minus 1 Which one do you want to find first? Go ahead.
Is the y is at 4?
Sorry?
Is the y is at 4?
Horizontal.
You like the y, you like doing the y first?
Yeah.
8 over 2 is 4, so yes, y equals 4 will be a horizontal asymptote. Horizontal.
Yeah, 1.
Vertical asymptote is, how do you write the equation?
2x minus 1 equals 0.
Okay, all right. 2x minus 1 equals 0, and that means x is 1/2, and you write it like that. You write the asymptote as an equation, x equals 1/2. Gosh. This is vertical, this is horizontal. So you go over to a graph, and you put those asymptotes in first, and you get, I'm gonna change my mind here and make this a negative. So we're gonna go out, here's one, we're gonna go out 1/2 and draw an asymptote, a vertical one. And we're gonna go out 4, or up 4. 1, 2, 3, 4. And draw vertical or horizontal asymptote there. That means we got to extend this one a little bit. And we're going to put them in the upper right, lower left, or upper left, lower right? Upper left, lower right, because I put this on at the last minute. See what I'm saying? Everybody clear? So in that situation where you have an x on the top and the bottom, you can't really read it for transformations like the previous example. So you have to follow to these other ideas. Set this equal to 0 to find your vertical, put this over this to find your horizontal. Okay? And actually, yeah, that's good. Okay. All right, so let's look at example 4. Because you can do this also. We learned this earlier. You have forgotten, but you learned it earlier. We can take a situation just like the one I was just presenting you, and you can turn it into a function that you can read for asymptotes. Consider this, 3x plus 5 over x plus 1. 3x plus 5 over x plus 1. That looks just like the one we just had, right? Hard to read in that form. Well, I want to show you something cool. You've seen this before. I know because I taught it to you if you were in my class. And I'm sure your other teacher did too. Instead of saying, okay, that's going to be 3 over 1 and negative 1, which is really easy to do. I'm going to show you another way, and you're going to have to practice this as well. You can take x plus 1 and divide it into 3x plus 5, because isn't that what that means? Numerator divided by denominator. And you know how to do this kind of division. You've probably forgotten, but this is how you do it. You take x and divide, you ignore that entirely. You take the x and you divide it into 3x. In other words, you're asking, what can I multiply x by to get 3x? 3. Then you take 3 times x and you write it here. And you take 3 times, in other words, you're doing a distribution. You're taking 3 times this, which would be 3x plus 3. Then anybody remember? Change the signs and add, which is the same thing as subtracting. Those should add out. This adds up to what? 2. So what do we do with the remainder when we're trying to write this whole solution? You take the remainder and do what? Put it over. Yeah, you put 2 over x plus 1. Do you remember that, what your teachers taught you in grade school when you were just doing this with numbers? That you take the remainder, put it over the divisor, and that becomes the fractional part at the end? You recall that? Can you see the result of dividing this into this is this, and so they are equivalent? This expression, this divided by this is this. So now I have the equation, y or g of x equals 2 over x plus 1 plus 3. Why did I reverse it? So you could recognize the transformations. But it's still the same thing. Put that on the front, put the 3 on the back, and now you can tell. We're going to go up 3. Okay. He's not here. Oh, yes, he is here. Did you bring a note?
Yeah.
Okay. All right, so I reversed this result of doing this long division, and now we can read it. It's going to go left 1 because this has not got an x in it anymore. It's just a number like we taught first. So it's going to go left 1 and up 3. Isn't that what you would have gotten here?
Yeah. I think the other way is easier.
Okay. It doesn't matter. You have to practice them both. Okay. So if it says figure out the transformations by doing division first, you do this. If it says figure out the transformations and graph the function, you can go immediately to that. But either way, you get a vertical at -1 and a horizontal at +3. Either way. But you need to know how to do both ways because it's gonna get a little more intense later. You need to know this little thing.
So on the bottom one, does the 2 mean like a
Vertical stretch of 2.
Yeah.
And that's one thing that this doesn't reveal. You can't see a 2 in here anywhere. This thing reveals a vertical stretch of 2.
So how would you get a vertical stretch of 2 out of the original?
Without doing this, you can't read it for that. You'll have to plot a couple of points and see how fat they make them. Just plot in a couple of points. So this one, you can get directly to the asymptotes directly from here without doing this, but you can't tell the stretch, so you'll have to plot a couple of points. Here, you do the division, and here you can tell what it's gonna be. It's gonna be the square root of 2, which is about 1.4, 1.5. As you go out, we'll tell you how to write this. So it's kind of 6 of one, half dozen of the other, because if you do this immediately, you're gonna have to plot points, which takes some time. If you do this, you won't have to plot points, but this takes some time. You need to know both ways. Okay? All right, last thing, example 5. We're gonna make it here. A 3D printer builds up layers of material to make 3-dimensional models. You knew that. Have you ever seen one work?
Yeah.
Just laying down little thin layers of plastic and just build it, okay? That's neither here nor there for the math, what we've got to do. So here we go, we're gonna hunt around for what information we've got to do something with. Each deposited layer bonds to a layer below it. Again, worthless information as far as math goes. Now, here it comes, and this gets a little rough to try to figure out. A company decides to make small display models of engine components using a 3D printer. Now, here comes the crux of it. We're not even talking about 3D printing at all, or scaling anything down. That's not what it is. It's talking about making money. Shh. The printer costs $1,000. The material for each model costs $50. The question asks, estimate how many models must be printed for the average cost per model to fall to 90. Oh, what? What is average cost? How do you figure average cost? Do you know what cost is? It's the amount of money to stay in business, or the amount of money to get this project done you have to spend. That's cost. Okay. How do you, in a general way, without looking at the information that's in this, we'll make it apply here in a minute, but how do you figure average cost per item? For every single model that you're going to print, how do you figure average cost? Exactly. It's very good. You find out your total massive cost and you divide by how many you printed. That will tell you average cost per item. Now I'm here to tell you, the very, very first one that you do will cost you, if that's all you do, is just one model, it'll cost you $1,000, $1,050. If you do 2, just 2, and stop there, each one will cost you $550. Because you split the cost of the printer between both of them, and then it costs you another $50 for material for each one. So just doing 2 brought the average cost down considerably, from $1,050 to $550 each. You see what I'm saying to you? If you were going to go and make 4 of them, they would each cost $300, because you take your $1,000 and split it up 4 ways, right? And then add $50. That's if you stop at 4. They were $300 a piece. Can you see that every time we add another model that we've made, that the average cost comes down? We want to know how many we're going to have to make so that the average cost comes down to 90. Right? Okay, now let's see if we can write an equation for that. In a general, well, I guess talking specifically about the prices and the cost function, the money spent in this, can you give me a cost equation for these? By the way, how many of these models are we going to print? So we're going to call it X, because that's what I've decided to put right here. This is the cost as a function of the number that we print. That's what X is the number of items we're going to print. We don't know that right now. Are you with me? So can you write an equation knowing that X is the number we're going to print, even if we don't know it, that will tell me total cost? What will it be?
1,000 plus 50x.
What'd you say?
50x plus 1,000.
Okay. That's how you want to write it. 50x. That's the amount of material. That's the cost of the material to print X items. Do you agree?
Yes.
50 times X, and then you have to add on that additional cost of the printer to begin with. So this is a line. This cost function is a line. You start out at $1,000 and you go up $50 for every one you print. This is their slope. This is your rate of change. This is where you started, the amount of money you spent. You with me? So this is linear, but this is not average cost. Speaking about the left side here, how would you express average cost? Total cost, which is this, right? Divided by X, and that's what Rachel said a long time ago that we've been working off of. This is average cost. Total cost divided by the number printed. That's average cost per item. You agree? Then this is equal to 50x plus 1,000 divided by X. Rational function. Fractional function expressing averages. So we get our fractional function here. Now you got to figure out, now that you finally figured out this part, which was new, now you see you got a rational function here. How are you going to deal with it to answer the question? By the way. How many? Well, we have to print so that average cost is, so this whole expression here gets replaced with 90. That's average cost, and this is our average cost function as a function of how many we have to print. So if we solve this for X, whatever that equation is, if we solve it for X, we should have it. We should know how many we have to print to bring the cost down to 90. How would you begin? Let me give you a hint. It doesn't have to do with the graph. Cross multiply.
Oh, wow.
90x equals 50x plus 100. That is not a hard thing to solve. It may have looked hard here, but as soon as you say, oh yeah, cross multiply, it's a great tool. Do that equals this. Now it's easy. 40x equals 100. X is 25? It's not 25.
It's 2.5.
Oh, wait, I forgot my zeros. Try that. Do that instead. That one is 25. So you need to print 25 models, and if you do, then that means their average cost will be $90 a piece. If you print more than 25, like 30, it's going to come down a little bit more. It'll be a little less than $90 a piece. You with me?
Mm-hmm.
But what is it approaching?
50 is the cutoff line, right?
Because
Because none of the items that you print can be less than $50. As a matter of fact, none of the items that you print can be actually 50, because this $1,000, even if you get down into pennies, is always shared by whatever you're making. This keeps getting split up. And then less of this goes to each one, but you'll never get to 50. So what we're saying here, folks, is if you were to graph the cost function, 50 up here, $50, where this is your cost, average cost, and this is the number of items that you make, there's going to be an asymptote here. And it started way the heck up here at $1,000, and it came down swiftly from there. But is approaching $50. It can't ever arrive because you have to keep sharing this printer expense among each one that you make. And the more you make, the less it is per printer. But none of them can ever be less than $50. You see? The more you make, the more the cost, the average cost approaches $50 each. But it can't get below that. So that's the answer to the second bullet point. What happens to the average cost as more models are printed? Average cost approaches $50. But you can't say it arrives at 50. It approaches 50. Okay, there you go. 2 assignments. They're both on Big Ideas Math. If you look on Power School and you scored more than 75 or more on the test, then you can start submitting your stuff on Big Ideas if you want. You don't have to. But if you scored less than that, you have to do your stuff on paper. And if you're in that situation and you don't have graph paper, you're going to want to grab that. There's some graphs in it. Okay. Oh, I've got to tell those people doing it on paper the assignment. Here it is.
Yeah.
The assignment for section 7.1. By the way, these are 2 different assignments. You're just getting them both today. Two different ones or zeros in the book. Okay, so the first assignment, 7.1, is, are you ready to write? 3 through 17 odd and 26. And then on 7.2, which is where you're actually dealing with the functions, this was a little longer. You ready to write? This is a whole bunch of hand-picked problems, so it's a list. 1, 7, 9, 13 to 19, odd, 21 to 24, and then this list, 25, 27, 33, 37, 41, 43, 46, 47, and 49. Because it took you a while to write, it feels like the daunting task, but it is. It's 20 problems, it won't take together. Okay? So you get a long weekend. Don't wait till Monday night at 9 o'clock to start this. You will forget how to do them. Do it in your history or English class today when you're done with their assignment, so that it's fresh on your mind. Okay? Not until your teacher says it. Make sure you get what they want you to do done first.
That was useful. Bye.